So welcome everyone. This is the Berkeley Institute lecture series. My name is Xie Chen. I'm a kinetic matter theorist here. Our speaker today is Professor Xiaogang Wen, who on the other hand, I don't think need an introduction. We're very happy to have Xiaogang with us. He's actually doing a sabbatical here until mid-April. So if you want to chat with him. He's sitting in bridge in office. I forgot the number, so you'll find him along the bridge entrance, sitting somewhere along there. And we're going to have the lecture series every Friday at this time, 1:30 until 3 throughout the winter quarter. So there might be a couple of weeks where we're gonna cancel the class, but almost every class for the winter quarter. The class is also hosted on Zoom. Here's the Zoom ID, and for everyone on Zoom, welcome as well. The lecture will be recorded on Zoom, and will be the recording will be posted on the PMA website, some YouTube website, I was told. That's all. That's all I want to say. And without further ado, please.
Yeah, thank you, Xie. Yeah, I really appreciate this arrangement. And for my visit to Caltech, which is very warm weather, and also arrangement, Xie and Hiroshi for arranging this lecture series. So in this lecture series, I plan to talk about mainly the generalized symmetry, which seems to be important. It turns out that the generalized symmetry is not described by group, but described by something else, which happened to be topological order. So that's also giving me a chance to discuss some related issue about the topological order. Yeah, certainly. Why you want to study generalized symmetry? Why that is useful? And so basically, so here's the motivation. You know, we want to study quantum matter, basically quantum many-body system in thermodynamic limit. So there are three kinds of quantum matter. And we can say that there's a gapped one, which have no low energy excitation. So such like they can be band insulator, quantum Hall states, and those kind of gapped quantum matter. There are also a gapless one with a few excitations, not too many. And so the example of this would be this like a Dirac semi-metal or wild semi-metal or superfluid, the critical point of continuous phase transition, those kind of thing is we call the gapless state. But those gapless states turns out to be so-called the liquid, the concept, which I will introduce in a moment. But it's not ordinary liquid, but there's a formal liquid. There's another kind of gapless matter we call non-liquid, which have a lot of excitation and which is kind of beyond the quantum field theory. So the liquid gapless matter are within quantum field theory, but the non-liquid is beyond the quantum field theory. And so they like a Fermi metal or Boson metal, those kind of things. And so certainly those kind of quantum matter can be divided into two classes, either weakly correlated or strongly correlated, or weakly interacting or strongly interacting, or maybe say the easier or hard. So that's kind of also belong to this two class. So so for the weakly correlated gap states, generally we just have a band theory. You know, the band theory just mainly emphasizing on this eigenvalue. We got a dispersion relation. However, if you also worry about the eigenvector, then the eigenvector may be twisted in the Brownian zone. So, and this twisting may be described by K theory that's led to the topological insulator. So that's a more complete theory for gapless gap theory. So this kind of dispersion, we have a gap. And so there's also weakly correlated gapless liquid states. And so like a band theory with the Dirac points, or you have a kind of boson condensation, it's a superfluid mode. And those things are generally described by quantum field theory. Okay. So then we also have this weakly correlated gapless non-liquid states. It turns out that the Fermi liquid is an example of this non-liquid quantum states. Okay, and for weakly correlated boson system, yeah, actually we don't know an example of this gapless non-liquid states. This is interesting to see if you have some example for weakly correlated system. Yeah, sure.
I just asked the first question. So why Fermi liquid is a non-liquid state? So
yeah, it's the liquid usually defined as it don't have no shape. But here the liquid is defined via quantum information point of view. So later I will define that, and then this definition, the Fermi liquid is not liquid. Okay, and so it's kind of funny. So it's actually Fermi liquid is I think more important to say that Fermi liquid is not quantum field theory. That's also a strange thing to say because well, free fermion certainly is quantum field theory. But when you have a Fermi surface, you ask for the low energy effective quantum field theory for the Fermi surface alone, without thinking about the whole band. Then things become very tricky. Actually, there is a quantum field theory for that, but you find you need an infinite number of fields. So actually, these non-liquid states turns out that their infrared effective theory usually have infinite number of fields. So they are really belong to a quite different beast, and so it's more complicated. So therefore, all the Fermi liquid almost is the first thing we teach in solid state physics, but actually it's maybe the last thing we understand. So it's more complicated than those gapless liquid states. So we make this distinction because in these lectures we mainly talk about the gapless liquid states. So we kind of exclude Fermi liquid, which is more complicated. And so there's also for the strongly correlated matter, certainly we have a strongly correlated gapped states. So a simple example of that would be this Gibbs-London theory for symmetry breaking. Then we have a group theory to describing them. That's a mathematical foundation. Okay. However, we also have a highly entangled liquid states. For those highly entangled gapped liquid states, then things are more complicated. So group theory is no longer enough. So therefore, the Gibbs-London theory is replaced by this topological quantum field theory, and the group theory is replaced by this category theory. So there's some category theory some enter into the picture. So that is strongly correlated gap states. But here we need a new mathematics really because we are dealing with entanglement. The highly entangled quantum entanglement has a much richer structure. So that beyond the symmetry, so we need that. Then we have this strongly correlated gapless states. And the typical example of this is a 1+1 dimensional conformal field theory. Okay. And so they're describing the critical point at continuous phase transition. But here we really have very poor knowledge in the higher dimension. In higher dimension, we don't have a general theory. And I may say, well, we have quantum field theory in any dimension, so why they describe the gapless states? Why we say we don't have no general theory? The things that for gapless liquid states, if there's a well-defined non-interacting quasi-particle, then they belong to weakly correlated version. So then we have a theory. Then when we say strongly correlated gapless liquid states, I mean the liquid state with no quasi-particle. There's no low energy non-interacting quasi-particle. Everything is strongly interacting. So certainly you can choose a quantum field to describe them where quantum field are strongly interacting, but this quantum field doesn't help you. It's just it's a mess. And so basically, I try to say that this gapless liquid state is described by a quantum field theory with no field. We don't know, with no proper choice of field. So basically, it's just I'd rather say no quantum field theory description. Yeah. So no Lagrangian or no good Lagrangian. So it's more of this kind of a thing. So amazingly, in 1+1 dimension, there's algebraic approach using conformal field theory. This some Varso algebra. We can deal with this kind of a gapless state with no quasi-particle using algebraic way, not using field theory way. And this kind of things are lacking in higher dimension. I think that actually that's the main motivation of this lecture. I don't have answer for that, but I hope some picture developed from this this point of view may help us develop this quantum field theory with no field and some way to deal with this gapless liquid states with no quasi-particle. So that's maybe the main motivation. Then certainly we also have a strongly correlated gapless non-liquid states. And well, actually, I don't think I really have an example of that. So there's some strongly interacting boson system with emergent fermion. An emergent fermion have a Fermi surface. So we may call this a strongly correlated bosonic system, which is not liquid. But the Fermi surface means we have non-interacting Fermi quasi-particle that's more or less also weakly interacting. So do we have a truly strongly interacting non-liquid states? I don't know. But that's also something very desired, because in high TC superconductor, we have this we seems to have a Fermi surface, but it looks like the relaxation time is comparable to the quasi-particle energy. So quasi-particle is not very well defined. So there's a desire to develop this non-Fermi liquid theory. And so this non-Fermi liquid theory in some sense is like a strongly correlated non-liquid gapless states, but without well-defined quasi-particle, whether such thing can exist or can be formulated. Oh, sorry. So therefore this, yeah, go ahead.
So when you say non-liquid states, it's strongly correlated. You don't mean having broken symmetries. You still featureless state?
Yeah, right now the liquid, non-liquid, basically, I think at this stage you can understood as so do you have a Fermi surface or not?
So non-liquid would be no Fermi.
Non-liquid means with the Fermi surface, and the liquid means you have Fermi point. You have the Lorentz symmetry. So those are entanglement structure are easier in some sense. When you have Fermi surface, the entanglement structure is more complicated. So that's reflected in the fact that the low energy effective quantum field theory should contain infinite number of fields.
So you're mentioning we got this non-liquid states. So having a Fermi surface but with quasi-particles that are ill-defined because their lifetime is so short.
Yeah.
Would it be common, you would think, or not, to have other collective modes that are long-lived?
Okay, yeah, that's an interesting thought. Maybe there's some other collective mode which are like quasi-particle like.
Yeah, like
then we can. That means that we should not use a Fermi, we should use other collective mode to do that. But sometimes maybe there's no other collective mode. Yeah, or maybe there are, but we don't know. And yeah, and I think in conformal field theory, we do have an example that there's no other collective mode. Yeah.
So is the spin-on Fermi surface an example?
Yeah, the spin-on Fermi surface will be this strongly correlated bosonic system, but which is non-liquid. So that means their entanglement structure actually is more complicated than Euro critical point, things like that. The Fermi surface indeed is a new feature, and it's a more complicated feature. And if we have a quasi-particle near Fermi surface, then we have a theory. If you don't have a quasi-particle, then it becomes more complicated theory. And so this time I try to focus on this gapless liquid state, which are simpler. Whether what we learn from this gapless liquid state can help us to learn this non-liquid state with the Fermi surface, I don't know. Yeah, but that's maybe yeah. That's the thing. So those basically kind of overview of what we have, and so then we try to consider this so-called gapless liquid state. Basically, it's a state with a low energization, have this Lorentz symmetry or something like that. And so the question is, how do we develop a general theory for gapless liquid state? That's the question. The first thing we need to know is we need to have is just find a label. We have to give them a name. If there's several of those gapless liquid states, we should give each of them a name, but not a name like a phase A, phase B, phase C. Something more informative name. Okay, so what is the proper name to name them? So actually, we are facing the same difficulty when we try to study topological order, how to give them a proper names. And here looks like the one way to give them name is using symmetry. You know that at the low energy effective theory, you will have more symmetry than the lattice UV theory. So maybe this emerging symmetry probably can characterize these gapless states. And in recent years, there's a lot of development, and we find that this emerging symmetry can be very rich. Can be the ordinary symmetry, can be this anomalous symmetry, can be the higher form symmetry, or anomalous higher form symmetry, or algebraic higher symmetry. But algebraic really means non-invertible, so some symmetry is even not invertible. So all these kind of crazy symmetry and their anomalous version. And so this became very rich. So we kind of, so here I just collectively refer all those symmetry as a generalized symmetry. Invertible, higher, they all kind of generalized symmetry. So because this generalized symmetry is very, very rich, so that's because it's so rich, and so then we start to dreaming. Maybe this generalized symmetry is not only characterize the gapless states, maybe it's even fully characterize the gapless states. At the moment, this thing is too strong. Probably don't fully, but maybe largely. We don't miss too much. And but on the other hand, whatever we miss, we can call the missing part even more generalized symmetry. So then at the end, the statement is still true. The generalized symmetry characterizes gapless states fully. Okay, and so therefore the idea is that using this generalized emerging symmetry as a starting point to formulate a theory for gapless liquid states. So that is the desire. Okay, so we know that the ordinary symmetry is described by group. So what theory describes other generalized symmetry, all those symmetry? Then turns out that all those generalized symmetry can be described by so-called non-invertible gravitational anomaly, and which actually is almost the same as a topological order in one higher dimension. Yeah. So this really the statement I make at the beginning, that all those generalized symmetry is not described by group, but by something we already know. It's by topological order in one higher dimension, or TKFT, or tensor category, or something like that. So that is a kind of a mathematical formalism to describe this generalized symmetry. And then so maybe this gapless states can be described in this way. Physically, it turns out that using topological order to characterize the symmetry, using symmetry to characterize the gapless states, it's basically like saying that the general theory for gapless liquid state is actually the boundary theory of a topological order in one higher dimension. Yeah. So once you know the symmetry, you can identify topological order in one higher dimension. The boundary of that topological order actually describe your gapless states. And so this is kind of a physical connection. So therefore, this study of a gapless state became a study of a gapless boundary of a topological order. So these two things may be very, very closely related. So that is basically it's kind of a picture and a program. We see whether they can yeah, at the moment it's just a beginning, so we hope we can run through it and this is where they can lead us somewhere. So yeah.
So this is the plan to show that Fermi surfaces emerge as an edge theory for topological order in higher dimensions.
That is even beyond this program. Fermi surface is a non-liquid. Right now we don't touch non-liquid. So we try to say there's a critical point, the phase transition, coming from the boundary of a topological order. And let me put it this way. The gapless boundary of topological order can fully cover all the possible critical point of phase transition. So this is a desire, the statement we try to make. Yeah.
So the question I wanted to ask is, would that be a unique description? Or is it possible that it's also a boundary theory for a different kind of?
Yeah, this is a very good question. I hope to address this question maybe in my 7th, 8th, or 9th lecture. but since you asked, so basically it's really following that certainly given topological order, there's many boundaries. Okay, so there's many gapless boundary of same topological order. Seems this it's impossible to use that picture to describe gap states. But however, the point is that given topological order, there's maybe one gapless boundary which have a fewest excitation. Okay. But no condensation, which I have to describe later. And so there's a one canonical boundary of topological order with the fewest excitation. So that one maybe is have maybe close to 1-to-1 correspondence with a topological order in the bulk. So the canonical boundary of topological order and topological order may have a close to 1-to-1 correspondence. But there's many other boundaries with a more gapless excitation. But that one you can say that one we did not discover all the emergent symmetry. That one has a more emergent symmetry. Actually, the same gapless theory can be a boundary of a bigger topological order. So there's a small big correspondence unit. For the given gapless state, we want to find the biggest topological order, biggest symmetry. For the same symmetry, we want to find the smallest gapless states, which don't have any other emergent symmetry. So with this kind of setting, maybe there's a 1-to-1 correspondence. But at the moment, we cannot claim it's 1-to-1 because the example we know is not 1-to-1. But maybe 1 to a few. If 1 to a few, that's already a progress. And this additional ambiguity, we have to study what is this additional ambiguity and whether we should assign additional emergent symmetry or whatever, But that's some kind of working in progress. Yeah. But that's really a very good question. Yeah. Yes.
So I guess frequently there are theories with anomalies, they cannot be, they really need to be realized on the surface of higher dimensional something.
Yeah.
Let's say Ising transition in 3 dimensions. So if it's realized in a 3-dimensional system, do you mean that somehow, I guess it has emergent symmetry, which is
so maybe I think we're going to talk about the Ising transition in 1+1 dimension. So we can view this as a boundary of a 2+1 dimensional topological order. And because Ising model have Z2 symmetry, this topology will be very simple, just a Z2 gauge theory. So boundary of Z2 gauge theory. And so there's a Z2 theory has a canonical gapless boundary which corresponds to Ising critical point. So that is kind of a thing. I hope this picture works in a higher dimension, but in higher dimension, we don't have a much example. But we have a lot of example in 1+1 dimension, quantum field theory and 2+ dimensional topological theory.
do you mean that it has extra symmetry, which in some sense cannot be realized in 2 dimensions?
Yeah. So in 2+1, so again in 1+ dimension, I think transition. I mentioned that it's a bulk topological order is Z2 gauge theory. But these two cases do not reflect all the emerging symmetry. There's a additional emerging symmetry in a icing critical point in 1+1 dimension. And so actually the larger topological order describing all the emerging symmetry is believed to be double icing topological order in 2+1 dimension. However, for 2+ dimension icing critical point, there are 3+ dimension topological. Whether that have a certainly one choice is a Z2 gate theory in 3+1 dimension. Whether there's a bigger, yeah, that I don't know. Whether there's a additional emerging symmetry. So we have to expand this Z2 gate theory in 3+1 dimension to something more complicated. That is not known. Yeah.
And emergent symmetry do not mean like when there is rotation, arbitrary rotation in space time.
Yeah, that's another excellent question. Is that so far what I'm going to talk about is mainly emerging the internal symmetry. There's also emerging the space-time symmetry, and in particular for this liquid state, there's emerging the Lorentz symmetry. And that certainly should be very, very important. And actually there's a lot of missing part I don't understand, probably coming from there. I did not include the emerging the space-time symmetry and Lorentz symmetry and the conformal symmetry. And so they should be included. But at the moment, I don't know how, but so mainly comes from the emergent internal symmetry. But that is absolutely crucial, yeah, to have more complete theory. Yeah. So basically that's kind of a motivation of this kind of topic. And so what I plan to do is first I do discuss this some microscopic model of a topological order, and then using this we can see they also provide an example of a higher form symmetry, and also then we'll develop this macroscopic theory of a topological order. But basically it's like an introduction for category theory, you know. And then we'll try to formulate this theory for generalized symmetry in terms of topological order or in terms of fusion higher category theory, which I really don't know what are they, but I can tell you some about what I understand through some simple examples. And so here, because of this topological order in one higher dimension is very closely related to the symmetry, so we also call this topological order in one higher dimension, refer them as a categorical symmetry. You know, so it's just kind of new point of view to look at the symmetry. And the last, then we will apply this emergent symmetry to study some gapless states. And here, the main point of view is that whether there is some other approach we call the number theoretical approach, and the reason for this is the following: in 1+1 dimension, we know that the scaling dimension is a rational number, and but usually when you compute these scaling dimensions, we can do large N expansion or epsilon expansion and things like that. But the compute a rational number or compute the integer number using perturbation is kind of strange, you know. And so therefore, if those scaling dimensions are some good number, then there should be a different theory to capture this scaling dimension. So maybe actually this so-called number theoretical approach actually is a conformal bootstrap, you know. Conformal bootstrap is belong to this type of approach. So at the moment, I think maybe this is a way to combine generalized symmetry and conformal bootstrap. Maybe it's a tool to handle that. There's a lot of development in 1+ dimension and also more impressive in higher dimension. So maybe that could be a direction to go. Okay, so any question? Yeah, so that's a basic introduction. Okay, so let's go to another one. Okay, so let's try to describe some kind of microscopic theory for topological order. And so we know that this the symmetry breaking is describe a lot of phase matter where we have a symmetry group of Hamiltonian and a symmetry group of ground state, which is a subgroup of a symmetry group of Hamiltonian. This pair of group describe a symmetry breaking phase. That's how we label symmetry breaking phase. That's two by a pair of groups. Okay. So so in the early days of high DC, there's a proposal. Anderson had a proposal using this spin liquid with a spin charge separation to describe high DC superconductor, where the holon is a charge 1, spin 0 boson, whose condensation led to high DC. So that's maybe one way to get a high DC. And but the spin liquid is something with no feature. So there's a challenge, or there's a problem issue how to characterize spin liquid. At the beginning, we find a way we can using this kind of strange 3-spin order parameter to characterize a spin liquid. So that's break time symmetry, but not the spin rotation symmetry. So this kind of thing called the chiral spin liquid. But however, using this model, we study some model, we find that actually there's several different chiral spin liquid with the same order parameter. So there's already point out this order parameter probably is not enough to fully characterize a spin liquid. So that's a sign something new going on. And actually, even before that, in a quantum Hall states, and we have a lot of 2D electron gas with a very precisely quantized plateau. And this plateau quantization became more accurate if your sample are dirtier. And so there's symmetry do not play important role here, except charge conservation symmetry, which is not broken. And so for quantum Hall state, you have a different plateau, then maybe the different phase matter, but with the same symmetry. Again, we cannot use symmetry breaking to describe them. So this really is motivation for this notion of topological order, just describing those different things beyond the symmetry breaking order parameter. So, but that just say what it is not. It's not a symmetry breaking order parameter, but the question what it is. So one way to have a positive description for this topological order actually is putting this the ground state on the system with no boundary, like a sphere or torus or genus to Riemann surface. And because this state have energy gap, but we can study the ground state degeneracy. It turns out the ground state degeneracy may depend on different topology of space. So that's something non-trivial. So maybe this may be a positive way to describe topological order. So the funny thing about this degeneracy is that actually the ground state are not degenerate. They are not exactly degenerate. They are splitting, but splitting vanishes as system time goes to infinity. This is different from the degeneracy from the symmetry. Degeneracy from the symmetry are exact, but this is not exact. This only became exact in thermodynamic limit. But however, they are not exact, they are approximate. But this approximate degeneracy is very robust, means that you can add all the dirts to the system where the degeneracy is not lifted. Okay. So it have this topological stability. So we call this topological degeneracy. It can only change after phase transition, not by any perturbation. Yeah. So this just a degeneracy not associated with the symmetry somehow. Then the question is, what is associated to? So in 205, we've realized that this degeneracy maybe topological order may be related to entanglement. So then because at the beginning, when we started quantum Hall state topological order at the beginning, that's like end of 1980s or starting 1990s. At that time, quantum information not very popular. So we didn't think about entanglement. And by 2005, the quantum information became very, very popular, became a fashion. Then we think, oh yeah, this entanglement actually play a very big role here. So we should think about entanglement. So it turns out that this degeneracy actually is coming from entanglement. This topological degeneracy coming from entanglement. This is maybe the key message. As you remember, when I was in MIT, the John Prisco come to MIT gave a colloquium. I think one thing I remember is that this entanglement means if you know every part, you still don't know whole. Yeah, that's the magic of entanglement. Yeah, and actually this magic gave us this topological degeneracy, because for example, for these just two qubit states, we have these plus states and minus states. If you want to look at the 1 qubit, you have the same entanglement density matrix, which is like this. So this entanglement density matrix from a single qubit cannot distinguish whether you have a plus state or minus states. So this kind of thing generalized. So you could have a distinct quantum many-body wave function. If you look at every local part of this wave function, they are identical, although the global quantum wave function is different. It's orthogonal. And so this is knowing every part still do not know whole is really what's behind this topological degeneracy, and also behind all this topological phase of matter. I think this is this thing. So this realization is very important. So we start thinking about the entanglement to see how to view topological order as some kind of a pattern of entanglement. So from this point of view, what kind of picture do we get? Okay, so let's try to think about the entanglement. At the beginning when I don't understand entanglement, I thought, what is entanglement? Entanglement is superposition of two different states. So every state that's entangled because every state can be expressed as superposition of every other two states. But actually, what I'm missing is that entanglement requires another structure, it's tensor product structure. So which is not very much emphasized in physics quantum course. The quantum mechanics not only is linear algebra, it's actually linear algebra with a tensor product decomposition. I think the second part is very important. So that is especially emphasized in quantum information theory. So therefore, a local quantum system actually is like this. We have a small Hilbert space. The tensor product of small Hilbert space gives us a global Hilbert space. And then we have this Hamiltonian is given a local operator which acts on this small Hilbert space and maybe nearby small Hilbert space. So this kind of a general structure of this quantum system. And then the ground state in this sense is not a single state of single system, because we take thermodynamic limit. So here we imagine we have a sequence of system with an increasing size. So when we say a ground state of a thermodynamic system, we're actually talking about a sequence system and a sequence of states. Okay. And this is also important to define what is a gap state. Because for the mathematician, every finite system is gap because the spectrum are discrete. Okay. But however, in physics, the gap system really describing a sequence. When you're taking n go to infinite limit, there's a window of a gap remain finite, and maybe some state below the window became more and more degenerate. This kind of a limit. So that's called the gap states. Okay. And then what is a phase? The phase are equivalence relation between ground states. But here, actually, the ground states are really not a single state. We should really say the ground state subspace is equivalent relation between two ground state subspace. And this equivalent relation, it can be described by this adiabatic evolution. If two ground state subspace can be adiabatic evolving to each other, we say they belong to same phase. And I think there's a theorem in quantum information theory that this adiabatic quantum evolution can be approximated by the quantum circuit, this local unitary transformation. So then we say that two ground states connect by local unitary circuit, they are equivalent. So there are certainly a lot of detail. This circuit should be finite depths and etc. So I will not really go into that. Okay. So from this point of view, we see that this gapped quantum phase are really just a sequence of a system. And for each system size, so we have two sequences of a Hamiltonian, non-dosible. And then for each size, we have a ground state connected by the local unitary transformation. So those and then we say these two sequences are equivalent. Okay, so that is that's a definition of quantum phase. Okay. So why go through this? Because I want to define what is a liquid. In this definition, we will see there's a problem, because this definition is okay if you have translation invariance. Because when you have translation invariance, there's no issue of increasing system size. You're just increasing system size by repeating this unit. However, now we say that symmetry is not important. Suppose we don't have translation symmetry. Then you have issue of increase system size. The system with two different sizes, maybe in different phase. So one is quantum Hall state, another is ferromagnetic state. That could be possible. So this definition doesn't have a problem. If you don't have translation symmetry, there's no horizontal connection. Okay. So therefore the quantum liquid is really trying to add some horizontal connection, how to increase the system size. And so in this case, one can generalize this equivalence relation. We know that the two states are equivalent if they are connected by local unitary. Now here we have to define the two states with different size are equivalent. What do we mean by that? So here we say that if you can dissolve product states, if you can add a product state to increase system size, then after doing local unitary to dissolve those actual product states into the system, and the whole process is seamless, we can do that. Then this is a liquid state. So in this sense, this topological order are really the quantum liquid state in that sense. It can absorb any product states. So in some sense, mathematics really means that the space-time geometry is I don't know what to say, that it's really have something to say about the space-time geometry. It means certain feature, some discrete feature. Yeah, we can say the lattice have a lot of features, but when you look at the lattice from far away, it's looking like a manifold. The manifold ignore those features, ignore certain features. So being able to dissolve these product states, it turns lattice into manifold, something like that. So there's some more cross-grain way to look at the space with we see less structure, and only those less structure are important. And so that's a liquid. So from this point of view, you can see that if a state cannot dissolve product states, that means some kind of a space-time structure should be included. And essentially, we know that this fractal phase have this correlation structure as kept. So that's kind of in line with this kind of picture. Yes.
Can you say why a Fermi surface would not have this property?
Yeah, Fermi surface cannot dissolve product states.
Is that obvious?
Yes, in a sense, when you look at the Fermi surface, the Fermi surface have those points, and the discrete point. And when you enlarge system, I don't know what to say.
Local space products.
Huh?
Not be described as a local and space products.
Yeah.
Right, that's logarithmic entropy.
Yeah. In a sense, let me put it this way: if you dissolve this product state is a gap, it's like you combine a small system with a gap state, then enlarge it, but then you don't increase the Fermi surface size. Yeah. So if a KF is a fixed not KF is fixed. The number of states enclosed by Fermi surface is fixed, then it's okay. But that's not our limit. Our limit is if KF is fixed. The number of states included in the Fermi surface is more and more, and we cannot do that.
Yeah.
Yes, so that is the reason. But then whether Fermi surface have a Fourier structure or not, or whether Fermi liquid should be viewed as a theory on the manifold or not, that's all interesting questions. And this is almost saying that maybe the Fermi liquid theory should not be viewed as a theory on the manifold, but on something, I don't know, this kind of crazy stuff, you know. But for fractal certainly is, we know the answer is not manifold, but Fermi liquid we don't know. Yeah, so that is that's issue. Okay, so certainly there's so one simple example for this of non-liquid states would be just stacking quantum Hall state together. You know, then it's a non-liquid. Okay, and another non-liquid is now the fractal states. You know, there's this Chamans have this model, and Haar here also have this cubic code model have a fractal structure. It's a really surprising structure, and I will not go into detail in this. Just to say that there's all kind of entanglement structure, and so Fermi liquid belong to this so-called S source introduced by Schwingel and McGreevy. That is so, for example, for liquid state, to increase their size, we just add dissolve into product states. Here, dissolving product state is not enough. To increase size, you have to make 2 copies of the same states plus some product states. Then we can increase size. And this cubic code is even stranger. We have to add something with this S2 states, you know. So it's it's kind of amazing. This entanglement structure is very, very rich. And in here, basically, I'm describing this, just say that I'm only consider those the first simple case, these liquid states. Yeah. Okay, so from here, then we can say that this long range entanglement will be this this topological order can be viewed as a pattern for entanglement. Certainly, the different shorter entanglement states means that means a shorter entanglement state means a state which can be connected to product states by these local unitaries. Then it turns out all the shorter entanglement states are connected by local unitaries among each other. So the shorter entanglement states only have one face. Then the long range entanglement state means the state which cannot be connected to local unitaries. Okay. It turns out that there's many different long range entanglement states which cannot connect to each other by local unitaries. Yeah. So that's actually this kind of this really entanglement picture of a topological order. So this really describes this a microscopic point of view of microscopic definition of topological order from this quantum circuit. And right now there's a big issue is that we guess the macroscopic theory is like a category theory. But how to derive the categories from microscopic? This part is totally open. Yeah, but at least we have a definition in a microscopic theory. Then there's a similar related thing is that when you have a symmetry, then even shorter entanglement states can be divided into many different phases, and this gives us so-called SPT states. So that is for shorter entanglement states, it's connected by local unitary without symmetry. But however, when you have a symmetry, you have to require your local unitary transformation to respect symmetry. Then maybe there are shorter entanglement states which cannot be connected by local unitary respecting symmetry. So that's give you this SPT states. So those kind of entanglement structure I'm going to talk about. So now let's concentrate on this topologically ordered states, means long range entangled states. So what is this simplest picture to build a long range entangled states? And certainly the product state is not long range entangled state. The single product doesn't work. So we want to do the superposition product state to build entanglement. But we cannot overdo it. If you consider all superposition, we basically get a state of a horizontal spin. Okay. So here the idea is that we sum over a subset of the configuration. Okay. So here's a lot of game one can play. And I don't know whether we exhaust the game or not. So one natural thing we can do string. We can say spin up is a background. We can say spin down from a string. Then we sum over all the loop of a spin down. So that's one way to select a partial configuration. Yeah. I can imagine you can select all the crazy sort of partial configuration. It may work. You get some new states. I don't know. Yeah. And for example, we can consider a state like a superposition of all loops with equal weight, or maybe superposition of all the loops with a plus minus sign, depending on if the number of loops is even or odd. Or maybe we can have superposition loops depending on phase factor raised to the number of loops. Yeah. And yeah, last one looks actually these two, the first and the second, looks maybe illegal, because you can write down such a wave function, but to know number of loops is non-trivial. You have to follow all the loops, so it's a global information. So therefore, when we say, actually that's a rule of game. Writing down wave function not enough. You have to argue that this wave function can be locally specified. Yeah. It turns out that the last one, this wave function cannot be locally specified. So there is no local Hamiltonian realizing that. Maybe only non-local Hamiltonian realizing that. But it turns out the first two are locally specifiable. But the second one only in 2 dimensions, not in 3 dimensions. You know, so those kind of interesting things. So there's a lot of game one can play here. And so those kind of wave function may have a long-range entanglement, maybe a way to build a topological order. Yeah, certain one natural thing is whether one can have fractal or some more interesting geometry. Certainly can do brane. The brane is easy. I can do, instead of string, can do brane. There you can get some higher gauge theory or things like that. And but whether something even beyond the string, beyond the brane, whether there's some other choice of a geometric object, you can build this long-range entanglement. But this kind of a description looks very artificial, and to have an experimental realization seems difficult. But actually, this string picture is not too far away from the experiments. In a sense, we can have this like a spin 1/2. They may pair into dimer due to this antiferromagnetic interaction. And then this spin liquid can be viewed as dimer liquid. And then the things that the dimer liquid and the string liquid seems very different, but actually they are very close. We can choose a particular dimer configuration like the red one as my reference. Then we compare every other dimer configuration with this red one, like this blue one. We will compare the two, just lay one on top of each other. We get this picture. Then you'll find that red and the blue form strings. So therefore, dimer fluctuation can be viewed as a string fluctuation. Yeah. So therefore, dimer liquid and string liquid are very much closely related. The only distinction is the following: in this string liquid, we have it's a superposition of arbitrary string. But in the dimer string liquid, it's a superposition of a certain type of string, basically close packed string. And so dynamics is somewhat different, but there is some relation. You know, so the dimer liquid may not be liquid, maybe become dimer solid. However, if you find a way to make it dimer liquid, then dimer liquid is a string liquid. So that usually gives rise to a long-range entanglement and topological order. And furthermore, actually, dimer liquid have also another feature, which is described this square lattice. That the dimer liquid in the first example on the Kagemann lattice, the dimer liquid corresponds to string liquid, which is unorientable string. The string is not oriented. But however, on this square lattice, we have very special dimer. the dimer always connect, you can give direction direction on each link from A sublattice to B sublattice. And then you can then compare to this this link, you can this red dimer and the blue dimer, you can say have orientation. So it turns out at the end it turned out to be this oriented string liquid. So then the thing that then for this kind of dimer liquid is orientable string liquid. So that's give you right to the U1 gate theory. Unoriented string give you Z2 gate theory. So yeah, this example just to say that just this a very rough consideration, you can get a lot of intuition and to get some kind of topological states. Okay. So this is so let's yeah, let's go to this this first two examples just a little bit more. So that is this so basically local rule is this so-called the local dancing rule. So the string can change its shape. So this is we have Hamiltonian which allows string to change its shape, basically. And also we allow we have Hamiltonian which allows string to reconnect like this, but with the same face. So those are kind of a dancing rule to describe a ground state wave function. Yeah. Okay. It turns out that both rules are local rules. So therefore we can design local Hamiltonian to specify this kind of rule in the ground state wave function in terms of projector, something like that. And then let's give us its global wave function, just a superposition of all string with equal the superposition of all loops. Yeah. And actually the second wave function also okay. We just modify the second reconnection rule. After reconnection, the two wave function have this minus sign. And this again something local. We can specify this locally. And then let's provide the second wave function. That's a superposition for all loops, but with a plus minus sign depending on even or oddness of loops. Yeah. So although counting how many loops is a global operation, but determining whether the loop is even or odd is a local operation. So therefore, this is okay. But interestingly, this local operation only works in 2 dimensions. In 3 dimensions, like this example, we have a string which overlap on top of each other, and then the reconnection here do not change the number of loops if from this example. So that means the second wave function is legal only for 2-dimensional loop liquid, but not legal for 3-dimensional loop liquid. Yeah. So there's some feature. It turns out that this first topological order is described by this we call the Z2 topological order or the Topological model. Really described Z2 gate theory. And the second one, this with a minus sign. This topology is a double Samian topological order. So it's double Samian is basically described as U1 cross U1 Chen-Samian theory. That's a low-energy effective theory. Okay. So we know that this the Z2 topological order can be realized by Topological model exactly. That's a soluble model. I think probably everyone is familiar with Topological model. But here I will describe this because this is also a good example for the higher symmetry. So let me go through this a little bit. Okay, and for the Topological model, we have 2 terms. One is we call the Q term, the U star term, and the plaquette term. This star term basically is a product of sigma z for the 3 link around a vertex. So here the spin live on the link, So basically, like we say, up spin is a background, the down spin is a string. So the product equal to 1. A Q equal to 1 means we have incoming string and outgoing string. They're always paired. So the string always connect, a string passing through vertex always connected. There's no end of string, basically. And this plaquette term is a product of X operator around a plaquette. That's flipping the spin. So adding a small loop or changing the shape of a string. So this is a string hopping term, and this is a string enforcing term, enforcing the closed string condition. Okay. And then these two terms, commute to each other, so this Hamiltonian is soluble. Okay. And so the many-bodies energy spectrum of Topological model basically is this. Because those operators commute each other, so ground state given by this common eigenstate of those Q operator and F operator with eigenvalue 1. So that's the ground states. Excited state correspond to some Q operator or some F operator have a -1 eigenvalue. Then that's excitation. Okay. So basically that's what I'm describing here. We have a quasi particle where the Q became -1 or F became the -1. The energy gap will be 2U or 2G. That's a quasi particle excitation. Okay. However, what is interesting in this model is that the ground states are really equal to the superposition of loops. But however, on the torus, we have 4 sectors because number of loops wrapping around the x direction, y direction can be even or odd. This distinction cannot be seen locally. If you look at the wave function locally, you don't know whether it's total even or total odd. But globally, that's crucial. The wave functions are very different for this 4 sector. They are orthogonal wave functions. So this is a kind of intuitive way to see that we have this locally indistinguishable states, but the globally orthogonal wave function. Okay. And here I just want to emphasize one thing is that although the operator Q and F can be +1, -1, but they cannot be -1, 1 by 1. If one Q operator became -1, there must be another Q operator also became -1. This -1 always appear in pairs, which I will explain just next page. But but this is important because those are topological extensions. They cannot be created alone. So that means from the experimental point of view, this the energy gap measured by thermal activation is 1/2 of the energy gap measured from a scattering experiment. So I think maybe this is probably the simplest way to determine this topological extension. The activation energy gap and the scattering energy gap is different. Yeah. So maybe so to see why this Q and F can only become -1 in pairs. Actually, we have these string operators because because those extensions are created by string operators. So for example, we can have a string operator, which is a product of a sigma x along these links. Then we can see that this operator commute with F and Q in the middle of string, but commute with F and Q. Actually, commute with the Q operator, this is Z, at the end of string. So therefore, Q operator at end of string is a flip sign. The sign is flipped. And so therefore, this string creates 2 Q operator extension. So that's appear in pairs. And another F operator extension is a string in the dual lattice. So there's also string in the dual lattice. Rather than connecting vertex, we're connecting center of plaquette. And the string in the dual lattice, we have a product of sigma Z. And this operator flip this F operator, sign F operator, and create 2 of them. So therefore, those topological extensions are created by strings. So this is maybe a general structure. So we say that this red string operator creating this type E particle. Okay. Then the string in the dual lattice, which got the Z string operator, creating this M particle. And then we can have a combination of 2 strings, the bound state 2 string, which basically is a red string plus it's a framing. the framing of a red string just displace red string a little bit. Then this displaced string can be viewed as string in the dual lattice, like this thin blue line can be viewed as string on this dual lattice. Yeah. And so therefore, we can have a product of X and product of Z based on this rule. And then this bound state of E and M, which give us a fermion. Actually, this F turns out to be the fermion quantum particle. Okay. So this really example for this the topological extension and the quasi particle. Okay. So I just mentioned this F particle is a fermion. So how do we determine it's a fermion? You know, certainly the string operator itself is a boson because there's spin flipping. It's a product of X, product of Z. This operator is a bosonic operator. But as I mentioned that the single string operator creates two particles. So each particle have a possibility to be fermion, you know, although combined is a boson. So to determine whether it's a boson or fermion, one can using this so-called hopping algebra. We can view the string operator as a hopping operator of this topological extension. You know, it's transfer particle from one string to another string when you apply this string operator. It's a hopping operator. So it's really a point of view that the statistics is not a kinematics, it's a dynamical property. It's determined by Hamiltonian. So the hopping operator determines statistics. So that's really based on this kind of a picture. And this hopping operator have some algebra, and this algebra of hopping operator determine statistics. So this is probably true. And recently, I think this picture is generalized to string extension. You know, string extension also you have operator which is changing shape of string. The algebra of this shape changing string shape changing operator can also be fermionic. So there define the notion for fermion can be some string can also be fermionic. So there's a story like that. But for the particle, it's simpler. Okay. So the way to do that, we consider four sites. This basically A, B, C, D. We have four sites. Okay. Then we apply. Then we assume originally we have two particles at the A site and D site. Then you apply this hopping from A to B first. Then hopping from B to C next. Then hopping from D to B. When you apply these three hopping operator, the final configuration is that A hop to B, hop to C. So this black one became here, and the white one from D to B became here. Okay. Then we can apply these three hopping operator in a different order. So here's a red, green, blue. Now we can do blue, green, red, just a reverse of the order. We'll do that. It turns out we hop a white one, D to B, B to C. So white one became here. Then the black one from A to B became here. You can see the final state have exchange. Okay. So therefore, so if this two order, this blue, green, red, and red, green, blue, it's the same, have same phase, then it's boson. However, if this two order of hopping operator have a negative phase, it's a fermion. It turns out that this one have a chirality, you know, this no chiral. So this phase can be e to the I theta. It's also fine. Then you get a anion. Okay. So and then we can check that so this combined string, this type F string operator, just mentioned. For this type E type M string operator is a boson, and type F string operator really gave us a fermion. Yeah. So this is the way. This hopping operator algebra is a way to determine boson on fermion. So maybe last I can try to using this example to discuss some higher form symmetry. Okay. So So the reason that this string operator create two quasi-particle rather than create something extended string like extension, really because the string operator commute with Hamiltonian in the middle of string. They do not commute with Hamiltonian only at the end of string. So therefore, when applied to the ground state, they only create something at the end. Middle part, they commute with Hamiltonian, do not increase energy. Okay. So another way to say that if this string operator from a loop, they will commute with Hamiltonian. Okay. And that is symmetry. So any operator commute with Hamiltonian is a symmetry. Okay. So this is so amazingly, this Topological model also is one of the simplest model to have a higher symmetry. Okay, which we'll really realize later. And so the higher symmetry have this property. They actually commute with any loops. Any loops. Hamiltonian commutes with any loops. So not like a zero symmetry. There's only one transformation. Here I have a bunch of transformation for arbitrary loops. They all commute with Hamiltonian. So that's a one character of a higher symmetry. Okay. So so because this higher symmetry, we can show that the Topological model have a ground state degeneracy just from this symmetry point of view. It's really because Hamiltonian commutes with loops, but sometimes this loop operator do not commute with themselves. And this is something also quite interesting. It turns out that for this kind of E loop and M loop operator, they have phase factor depend on number of crossing. But when we have two loops, the number of crossings is always even. Okay, so it looks like this is just nothing. You know, it's always even. So they commute. But actually, this is true only for contrastal loop. For contrastal loops, their number of crossing always even. So this relation have no meaningless for contrastal loop. They are meaningful only for non-contrastal loops. So therefore, when the space-time have space have non-trivial topology, we have a non-contrastal loops. And then like an E loop in X direction, M loop in Y direction. And then they have only one intersection. Then they do not commute. But however, both loops commute with Hamiltonian. So that means the ground state subspace from a repetition of this algebra. And this algebra have only one irreducible representation, which is two-dimensional. So ground state degeneracy must be 2. But turns out it's a 4, because we have another set of relation. One is E in X direction, M in Y direction, or Y in X direction, E in Y direction. But anyway, there's exchange X and Y. So you have two sets with anti-commuting algebra, which give us 4-4 degeneracy. So that's one way to understand the ground degeneracy or Topological model coming from this algebra. Yes.
So this symmetry seems to be very special to a specific model.
Yes.
But you want to describe something more general beyond specific model. So how much of this survives?
Exactly. So this is the this is a thing. I saw same thing. And in condensed matter, we don't have this kind of symmetry. Why we care? It's just totally theoretical. And but unfortunately, or maybe fortunately, is this one can be emergent. So we don't. So actually, this higher symmetry can be emergent symmetry, and so they became useful. And maybe that's the answer. So therefore, so I almost want to say that whenever you see gapless states, there may be emergent higher symmetry there. And then including all those emergent symmetry and emergent higher symmetry and all other non-invertible symmetry together, collecting all these emergent together, maybe that's a kind of specify the gapless states. At least we have a lot more information. And
is that signal known, or is it a conjecture?
It's a conjecture, yeah. And there's a reason why this is maybe true, yeah. At the moment, I can say it's conjecture or maybe wishful thinking, whatever. It's really try to say we have so much symmetries, and then we start to wish the symmetry may specify gapless states completely. So we'll see how much this is okay. Yeah, it's I'm trying to say this may be a interesting direction to think about. Yeah, but because but certainly we have an example. The higher symmetry is emerging. We have those examples. Yeah. Okay. So okay. And so what is interesting for this model is that when you describe degeneration this way, you allow to add a perturbation to the Tor code model. So you can add some impurity here, an impurity here. As long as the impurity leaves some channel connecting in X direction and Y direction, leave some channel open, you have string operator in that region, which anti-commute. Then you have exact ground degeneracy. Yeah. So for at least for those impurity, for those non-connecting impurity, the ground degeneracy is protected. But actually, the statement is stronger. Even when the impurity all connected, basically, even when you break those higher symmetry at the lattice level, the ground degeneracy still survives. So it became an interesting situation. Do we think ground degeneracy coming from symmetry or not coming from symmetry? At the beginning, I think it had nothing to do with symmetry. If you break all the symmetry is still there, so it's topological, it's not symmetry. But now we start to change our opinion. And actually, we are writing a paper about this. Is that maybe this also known that this emergent higher symmetry is always exact. Yeah, this whenever we have an emergent higher symmetry, then at the low energy we have a higher symmetry. But they have not only there is that they are exact, really exact. Really exact means solid. For finite system, they are not exact. But as system size go to infinity, they became exact below certain energy scale. And this is true, seems this is true for higher symmetry, but not for zero symmetry. For zero symmetry, this is not true. For zero symmetry, we may have emergent symmetry below certain energy scale, but this symmetry may be approximate. As you lower the energy, they become more and more accurate. But for any finite energy, they are approximate. And so this is originally I thought that maybe this is a general feature for emergent symmetry. Emergent symmetry means they are approximate. They became exact when the energy go to zero. But the emergent higher symmetry is different. That is, even for finite energy, they became exact, but in thermodynamic limit. The symmetry breaking term is expressed by system size, not by some power of energy. So therefore this exact emergent higher symmetry, you can use that to explain the degeneracy. Yeah.
So is this the same just for gas states or for gapless states as well?
Yeah, that's probably even true for gapless states. Yeah, and but certainly to prove that for gapless states is more challenging. And this is really kind of beyond my mathematical skill. There's physically is really that in the Coulomb phase we have an emergent photon. We know that emergent photon is topological. We can add any perturbation to the lattice model. We still have gapless photon. So this is a sign that this even for gapless phase, this emergent continuous symmetry remain to be exact. Yeah.
For liquid.
For liquid, yeah. Dimension matters. Actually, for non-liquid states, it's like effectively reduce dimensions. So maybe lower dimensions, this thing may not work. Yeah. But anyway, this Yeah, certainly there's a lot of issue. For example, for discrete symmetry, maybe this is statement true even for one dimension. Maybe for continuous symmetry, probably you need a higher dimension. Yeah, there's many details, but in generally, this is a feature. Yeah.
And this is not just for one form.
Yeah, for any this. So amazingly, that's a I find it's quite interesting because only zero symmetry is special. So the impression from zero symmetry is wrong actually, and for higher symmetry, even for non-invertible symmetry, I think is true. For higher symmetry, they're all exact. The only zero part. Suppose you have a lattice system with both zero symmetry and higher symmetry, and then when you add perturbations to break them, then you find the zero symmetry part may be broken weakly, but other part would survive. And so that is a picture. So only zero symmetry is broken by lattice. So because of this, so maybe this higher symmetry became more useful to study low energy dynamics. Yeah. Okay. And so maybe this is my last slide here is that so because this okay, let me put this. So it turns out this two symmetry called one form symmetry. Yeah, they call it one symmetry because they are generated by the codimension one extended operator. Yeah. So if symmetry applies for every site that codimension 0, that's zero symmetry. In two-dimensional space, we have loops that's codimension 1, they call it one symmetry. So for the Topological model, we have a Z2 one symmetry of E type, another Z2 one symmetry of M type. We have two one symmetry. Okay. It turns out that the ground state spontaneously break these two one symmetry. Okay. And then here there's an issue. What do you mean by spontaneous breaking for one symmetry? Okay. I think there's many definitions. So here we'll follow one definition that the symmetry is spontaneously broken if the symmetry transformation is not proportional identity in a ground state subspace. It's like in like ferromagnets, spin down, we have spin up, spin down. Certainly, the symmetry operation is trivial if you act on the spin up plus spin down. But the real spin up will transformation, you can spin down. So there's a non-trivial action. Okay. So here similar. So as long as in the ground subspace, the symmetry transformation is not proportional identity, then we say the spontaneously broken. And this is true and for these two states that even for the Z operator, we have 4-4 degeneracy. And this string operator sometimes is 1, sometimes -1. So they are not identity. And so therefore this 4-4 degenerate ground state can be viewed as a spontaneous breaking of these two Z2 one symmetry. Okay. So so therefore, yeah, we go back a circle. Topological introduced try to go beyond the Landau Ginsburg, and now we come back to Landau Ginsburg. So this is also is a spontaneous breaking of a higher symmetry, and we also understand why ground symmetry is exact, because emergence of a higher symmetry is exact. So therefore, their spontaneous breaking also provides exact ground state. So there's another way to understand the robustness of a degenerate ground state from exact emergence of a higher symmetry. But this is not true for zero symmetry. Okay. And actually there's a kind of this definition, and there's another thing is that we can say that the ground states is a symmetric, if they are not degenerate. And this sounds like a trivial statement. To define, let me see. Okay, to define a state symmetry or not, it seems very easy, but somehow it's sometimes not easy. Because sometimes later we'll go there. That sometimes we define the symmetry not using symmetry transformation, using something else. So we don't have symmetry transformation. Then to determine whether that symmetry is broken or not broken became tricky. Okay. And then here there's a more general way to determine whether symmetry is broken or not. That is, if your ground state is non-degenerate on any space topology, then you are sure that ground state is a non-degenerate. So actually, this picture is also important in the sense that that also means that state is a product state. You can see product state is a notion of a microscopic theory. We have a lattice. But when you talk to mathematicians, they have no lattice. They want to have a macroscopic definition for everything. Also in quantum field theory, is similar. So how do you define the product state in quantum field theory, which you don't have UV completion, you don't have cutoff? The one way to do so is that if you put your quantum field theory on the space with arbitrary topology, you show your quantum field theory have a non-degenerate ground state, you can claim your quantum field theory have a product ground states. So this is kind of similar. So this is a more general notion. Okay. And so so that's basically the point I want to say. Yeah. So maybe in next week, so we'll go into a little bit more about this higher symmetry, about their charge operator, and this also became an example of anomaly and etc. Yeah. Then yeah, maybe yeah, we'll end here. Yeah. So any questions? Yeah.
Is it obvious why the emergent higher form symmetries are always exact? Like what protects that doesn't protect the emergent zero?
Yeah. Yeah. So yeah, here just making a statement. I think to have a more general description, and you develop this holographic picture, so you can see more. But one simple way to see this, maybe almost make it trivial, is that for the zero form symmetry, the charge creation operator is a point operator. Okay. For higher form symmetry, the charge creation operator are kind of extended. And let me see. So to break symmetry, you need to create a charge. But this extent not only contractible extent, it should be non-contractible extended. A small loop don't break higher symmetry. You need non-contractible loop to break higher symmetry. So you need to add operator for non-contractible loop to break it. And so from here, that's non-local. So that's ruled out by your assumptions. And so this is I think that's a key difference. Yeah, to create a non-zero charge, you need this large loop operator. Yeah, and there's other way to see this. Is let me see whether we have some reference here. Yeah. Okay. I think in these two papers, there's a kind of mathematical physical way to prove the exactness of ground degeneracy. And if you follow the proof, there's you can see the shadow or sign of those emerging higher symmetry. Because when you show that the ground degeneracy is robust against any perturbation, that's almost the same proof can be used to show the emerging higher symmetry is exact. So these two are very closely related.
And this is independent of the topology of the space-time?
No, yeah, it do not depend on topology space-time. No, the proof, I don't know. the proof itself may depend on that, but the physics, we think do not depend on that. The idea do not depend on that, but the actual proof, sometimes you may use some trick which you depend on based on topology. But we think that as physics, they should be generally true. Yeah. Okay, yeah, I think we should end here. Thank you.